Prim's algorithm. So, here is the graph for Prim's algorithm. These are the steps to find the minimal spanning tree. Step 1, sort all the edges from high weight to low weight. Step 2, find all the edges that connected the tree to the new vertices. Then, find the least weight edge among these edges and include it in the existing tree. If including that edge creates a cycle, reject that edge. Step 3, keep repeating the step 2 until all the vertices are included and minimal spanning tree is obtained. We need to delete this edge because the graph will still be connected to the other vertices. Let's move to the next edge. This edge will also be removed because the graph won't be disconnected. The edge HK also can be deleted since it won't affect the graph. We can't delete this edge because K will be isolated vertex. The graph will still be connected even though the edge BF has been deleted. So, we are going to discard it. We can't delete this edge because K will be isolated vertex. The graph will still be connected even though this edge has been removed. Same goes to this edge, the graph will still be connected to the other vertices even though it has been deleted. The edge DH also can be deleted. We can discard this edge too. We must keep this edge. Please remember, we need to stop as soon as we have n-1 edges remain, which is 11 edges remain. And for this edge, we can keep it.
The rest will turns no because there's already 11 edges added to the minimal spanning tree.
We have successfully obtained the minimal spanning tree of the given graph. We can also calculate the weight of this minimal spanning tree by adding the weight of the edges. As you can see, the total weight of this MST is 33.
Kruskal's algorithm. I'll be discuss about Kruskal's algorithm, which is used to find out minimal spanning tree. We are using the same graph for the Kruskal algorithm. Minimal spanning tree is a collection of connected edges that include every vertex in the graph, but that do not form a cycle. Many such spanning trees may exist for a graph. The minimum spanning tree is the one whose cumulative edge weights has the smallest value, however. Think of it as the least cost path that goes through the entire graph and touches every vertex. For Kruskal's algorithm, we need to arrange the edges of graph in order of increasing weight, which is, from low weight to high weight. And for Kruskal algorithm, we are using add button. By using the formula v-1, we need to add edges which does not result in a cycle forms until v-1 edges are added. Step 1 says, sort all the edges from low weight to high weight. To make it easier, we can make a table for the edge, weight and add button. Also, we can see all the edges has been arranged from the lowest weight to the highest weight. Let's move to the step 2, pick the smallest edge. Which is, DE. Being the first edge obviously does not form any cycle. The edges represented by the blue lines are the one that are part of our minimal spanning tree. HI will also be a part of the minimal spanning tree. Next, CD. Adding this edge to the minimal spanning tree doesn't form a cycle. So, it will also be a part of the MST. Same goes to the EF. This edge can be added to the MST. This edge will also be a part of the MST. The edge BE will be a part of the MST too because it does not forms any cycle. Now, pick for GH. Check for cycles. If there's no cycle formed, add this edge to the MST too. Again, adding this edge to the MST doesn't form any cycle. So it will be added to the MST. If you add this edge to MST, as you can see it forms this cycle. So, this edge won't be a part of the MST. Next is CG. Again, no cycle being formed. Add it to the MST. Let's look at EI, C, A, D, H, and F, J. All these edges can't be added to the minimal spanning tree. Because adding all these edges would form a cycle. Now, pick for LI. Check for cycles. No cycle formed and add this edge to the MST too. Let's try add BF. It forms a cycle, so it won't be in the minimal spanning tree. One more to go. So, let's try add GK. As you can see, it doesn't form any cycle. Note that we are keeping a track of the number of edges in MST because according to the step 3, we need to stop as soon as we have v-1 edges, which is 11 edges to add. The rest will turns no because there's already 11 edges added to the minimal spanning tree. We have now the minimal spanning tree. Last but not least, we have to calculate the weight of this MST by adding the weight of individual edges in this tree. We can see that they add up to 33. So here's the comparison for the minimal spanning tree of Prim's and Kruskal algorithm. The total weight of minimal spanning tree for Prim's and Kruskal algorithm must be the same. And that's how you know you have the right answer. We can see the differences between Prim's and Kruskal algorithm is, they have a different button. Which is, Prim's is using the delete button and for the Kruskal, it is using the add button.
On October 9th, by using the Google Meet, both of us has been planning on how we are going to do this case study. We started solving the question on October 10 until October 11th. For the Prim's algorithm, it has been solved by Dayanku. Meanwhile, Scarlett solved the Kruskal algorithm. On October 11th, we had another conference meeting to compare our answer for the both graph by using Google Meet. From October 11th until October 13th, we had completed all the question by referring to the worksheet. For October 13th until October 14th, we had a discussion on how to present the ideas to show all the steps. We had started creates this presentation video on October 13th after we had the discussion, until October 17th. And the Gantt chart for the implementation of this case study has done by Dayanku on October 18th. These are the issues throughout this case study. The lack of in-person interaction with the group partner. It would be easier if we can discuss this case study face to face. And we both have a poor internet connection sometimes. Although it was a bit difficult, but we managed to complete all the tasks together.